my name's Dustin Dannenhauer, I'm happy to host with everyone else the second annual MIDCA workshop. So this is coming to you from the Collaboration and Cognition Lab at Wright State University. And I just want to thank the sponsors who have funded MIDCA research over the years: NSF, ONR, Army Research, and the Air Force. And I've had a lot of people from different universities contribute over the years, from Wright State, Maryland, Lehigh, and Union College. So what I'm doing now is I'm just going to give an introduction, and then we'll get started. So I wanted to just talk about the objectives from last time. So last year, almost exactly a year ago, we had the first annual MIDCA workshop. The objectives we had. So one of the things we wanted to do is to create resources, which was pretty great. So we now have about 8 to 10 videos of the talks that we had last year, and we're going to have the same thing from the talks from this time. To build community. So a few different people have started using MIDCA for different research projects, and we wanted to bring them together and have a chance where we could all discuss the project. The other thing from last time was we got a new user perspective. So for new people, we had a demo of someone using MIDCA for the very first time and how that process was. And it was also just the kickoff. So objectives for this workshop is largely similar. So we want to. Oh, I'm going to mute. Just give me 1 second here.
Oh, there we go. I can hear you now.
Great. I'm just going to mute you, James, if that's okay. Sorry about that. Still getting used to the Google Hangouts. So that was James Boggs. He's going to be one of our remote speakers coming from Union College in New York. And he's going to be talking about rebel agents. Should be an exciting talk. And we have Martin and Ryan joining us from DSTG Australia in Adelaide. It's Friday morning there for them. And Ryan will be giving a talk a little later. So over the last year, some of these new people have joined us, and so we wanted to welcome them and be able to have a conversation, have a workshop, and share new research results. And the other thing about this workshop is MIDCA has gotten a little bit more traction. So the theme of this workshop is kind of how does MIDCA shape up in the whole realm of cognitive architectures and AI, and what are we thinking about for the future? Talk a little bit about that. So the schedule is the following. So we have the first session. So we're in the introduction right now. After this, Mike will give a talk on cognitive architectures in MIDCA. And then we'll hear from Shravya, followed by James, and then I will give a talk, and then we'll have a 20-minute coffee break. So part of that coffee break is a little bit of a buffer of time in case a few talks run over, or if we have any questions. So if you're watching us live on YouTube, please feel free to type any questions you have. We see those in the chat. Know that there is some delay. So it might take a minute or two for us to get back to you, and that's one reason, why we have a nice long 20-minute coffee break. In the second session, we're going to hear from Ryan, followed by Venkat, Sampath, and Zora. And then we're going to have a discussion. So this was something we had last time. We had a long, like 45 to 50-minute discussion at the end, and that is a great time. So if you don't get to ask a question, or you're kind of wondering about something, or you have some comment, something you think is interesting, save it, write it down, and bring it up during the discussion. So during the discussion, we'll have a chance for everybody to talk about that. And then we'll have the closing. So, and we hope to end by 8 p.m. So for those of you who might be new, what is MIDCA? So MIDCA is, it stands for the following: Metacognitive Integrated Dual Cycle Architecture. Designed from the beginning for metacognition. So this is an architecture for designing artificial intelligence agents to interact in a world. The dual cycles refer to cognition and metacognition, and they're integrated. They share a memory, and there is an architectural model, a formalism that's been described in a number of research papers, and we have a running implementation. So we have Python, mostly Python software, that has implemented MIDCA so far. So I'm just going to go through the cognitive layer briefly. essentially there are these 6 phases. So the agent perceives the world, you see here on the bottom right, which is part of comprehension. So it perceives the world, it interprets the world, it might note something unusual, it might generate a new goal it would like to pursue or consider pursuing, and then it evaluates its progress on its goals. Solving side, intend is where the agent decides what goal it should pursue, if any. And then the agent, once it knows what goals it's going to pursue, it'll generate an action or a sequence of actions to execute in the world to achieve that goal. And so this cycle continues, and these phases work with a shared memory. The thing about cognition is that this is dealing with the world. So it's perceiving the world, it's interpreting, what's unusual around me in my environment. Are there obstacles? Things like that. The metacognitive layer, which, as you may note, it looks similar in structure to the cognitive layer, is instead of dealing with the world, it's dealing with cognition. So if you notice, perceive becomes monitor and act becomes controller. So it's now monitoring the cognitive layer, and it's interpreting if something unexpected is happening at the cognitive level. And so we see similar cycles here with intention and planning and controlling, where we might modify something at the cognitive level. So that's kind of an overview of the formalism. What's new for MIDCA over the last year? So if you look at our GitHub repository, we have about 100 to 150 commits. A good chunk of those are for the website, a lot of small edits for the website, which we have at midca-arch.org. So feel free to go there. A webpage for this workshop is up there. We've also moved repository locations. So please note that the new MIDCA repository is at colab2/MIDCA. And another thing here, the second bullet point, Python setup.py develop. For anyone who's developed MIDCA, there was this tedious interaction where anytime you change the code, you had to run Python setup.py install, and that's been fixed now. So to run MIDCA, you just have to do setup.py develop, and then any edits you made are already reflected when you execute it. Meta Aqua, which is in itself a whole research project, has been added. It does explanation among some other things, and more documentation on that is coming soon. And there have been a number of publications. So over the last year, these are some of the publications that have come out. The other thing I want to mention is for those on the live stream, you can rewind if you need to. So if you feel I went too fast over a slide or you want to know some details, feel free to just pause the stream at whatever slide you want to look at. So I'm not going to go into more detail about these. And so another thing is MIDCA's website. So we have, so this is great. This is a nice addition. It's using GitHub Pages, and this is kind of a shameless plug. Please, everyone, contribute to the website. So the website is just in the repository, right where MIDCA's code is. You'll see a folder MIDCA. There's a folder called docs. And so underneath docs, index.md, that's the homepage. So for example, it's kind of bare right now. So feel free to, we could really use a page with all the publications on MIDCA. So if you want to add that, it should be easy, and it's right there. So, and then finally, this is my last slide of the introduction. I just want to say, one thing we want to do is we want to make development on MIDCA easy. So if you want to run MIDCA for the first time, this is all you have to do. Clone the repository from GitHub, run this Python setup.py develop. You will need Python 2.7. CD into the folder, and then you can run an example. And my personal recommendation that I've started using this year is PyCharm for a Python editor, which is great, and it's because MIDCA has a lot of different files. So that's the introduction. I'm going to wrap up, and we're going to go ahead and get started with our next speaker, which is Mike Cox, and he's going to be talking about in MIDCA. So just bear with me a minute while I switch over to his talk. And I'm going to pass off the headset to him.
Thanks, Dustin. That was great and very wonderful. I wanted to add one other thing. Yeah, thanks. One other thing to the new additions. Let's see that. Oh, now I just spaced it out too. I should. Well, I'll come back to that as I remember it. Hopefully, Dustin had actually asked me late last year to talk a little bit about MIDCA and cognitive architectures and put it into context. There are a number of other cognitive architectures that have been in existence for over 30 years. A couple of them, SOAR and ACTAR in particular, go way back, and they're very mature and sophisticated. And I think we see some of that, and we call ours a cognitive architecture as well, but it shares a lot with it. But I want to try to highlight a little of the similarities and some of the differences with that. So I think one of the ways to think about cognitive architecture is to also consider other kinds of architectures. For instance, just a computer architecture, or even just an architecture of a building. We have a blueprint. Blueprints determine where rooms are, what the layout of a building would be, what its external structure is to the environment, but not things like where furniture goes for the most part. A lot of details then are populated by the owner of a house after it would be constructed. But the architecture defines the important structural things and functional aspects and the aesthetics for an overall design. Similarly, in computer architectures, we have a fixed set of characteristics. I do want to say that this is taken from the old Intel 8080. I think that was the original IBM PC was using that. So this is extremely old. Some architectures think of it a little bit differently now, but for instance, pipeline architectures. But here we can think of an architecture as containing functional components, and the 8080 shows a few of those. And then the data paths, how they're connected, which one provides data for others, and a representation for the data, and an instruction set to perform computation and changes. Then the user on an implemented chip or system that has come out of this architecture, a person would then be able to model something in the world and using a program or a language that then gets mapped to that instruction set and run under that architecture. So cognitive architectures are similar. They provide a fixed set of functional units, the connections, and often a representation in a language. We'll talk a little bit more about that and how some people have specifically described that. Excuse me. So there's also a number of other related concepts that we hear too. We hear not only cognitive architecture, but cognitive systems. And in fact, there's a conference that we published in a number of times called Advances in Cognitive Systems. They have a journal as well as a conference each year. I think the current one's coming up at Stanford, and it is the 6th annual Advances in Cognitive Systems. So what's the difference, between a cognitive system, cognitive architecture, information processing system, a cognitive agent, a goal-driven agent, or autonomy, reasoning? These are all related. So I will not focus on all of these, but some, particularly cognitive systems, it's a little broader. Pat Langley actually published in 2012 a really interesting paper. If you haven't seen it, you should read it. It's on the web and it's publicly available. He has defined 6 fundamental assumptions for cognitive systems that distinguish it from other AI systems. We go to AAAI, and there are a minority of papers presented on cognitive architectures or systems. Not all cognitive systems model from a cognitive architecture point of view, but they do usually assume that they're modeling high-level cognition rather than a low-level cognition, and often humans' intelligence rather than animal intelligence. So there's some differences there. Yes, a pause.
Sorry about this. This is we just need to change over.
So did that not get broadcast then, the slides? Okay, I can go back. That's still early. Okay. For those that missed, whoops, I'm going, hang on. All right, there was the architecture, related concepts, and then now about cognitive systems. So there were 6 basic assumptions that Langley outlined for the community. One was commitment to high-level cognition, another structured representations, often complex hierarchical representations. In cognitive systems, it's basically, it's not a bit vector or a simple vector of numeric values. Rather, it will be schemas or other hierarchical symbolic representations are the commonality for a cognitive system. Also, rather than optimizing, it is building a system that uses heuristics like people do. We often don't have complete and consistent, we don't do, well, let me see, I should just say often our solutions to problems as a human are good enough. That is, that they're satisficing and they get us through, they solve what we need in terms of a solution to a problem rather than the optimal perfect one. And there are reasons for that. But there's also a number of links to human cognition. Many of the cognitive architectures actually model human data, in particular MIDCA actually does not have a big commitment to modeling human data per se, but it is inspired in many ways by human performance and human behavior, and has certainly a relationship there, but we don't model in particular data that would be collected from human subjects, for example. And the research is often exploratory in that certain theories, certain cognitive architectures have a theory of how cognition might work, and are exploratory in the fact that often they're early, well, it's not simply preliminary, but they're looking at a very complicated space and testing hypotheses in a way that often are not as formal, and they can be rigorous, but they're not often as narrow. They're broad hypotheses that test in more of an exploratory way. And I think this paper will explain that more clearly. And though there are a number of cognitive architectures, I'm going to list 5 here, and I apologize to many EPIC and many of the other architectures that are out there, but 5 that are I will briefly discuss today in terms of the relationship to MIDCA are ACT-R, which is out of Carnegie Mellon University, SOAR, University of Michigan, and it originally came out of CMU, Icarus at ISLE, and Clarion, Ron Sun, that's RPI, and MIDCA here. Icarus, as far as I can tell, doesn't actually have an acronym. I did want to mention too, SOAR, that was the original acronym, State, Operator, and Result. I believe that is no longer the case. They use it less as an acronym now, but I thought I would put it there for historical purposes. I want to broadly look at each very briefly and look at what their commitments to a cognitive architecture means in a very small way, usually through a quote. So I have listed in this presentation, I mentioned, I think the slides are going to be made available afterwards as well, but I've listed a number of publications that give you a little bit more details about what we're talking about, and some links to all of these architectures. The URL is provided as well. So back in 1991, there was a workshop or symposium at Carnegie Mellon that was held on architectures for intelligence. And there, I think ACT-R, SOAR were both presented, as well as Prodigy, and Tom Mitchell was there. I don't remember, Theo, I think, was the architecture. John Anderson had a chapter, the very first chapter actually in this book that came out from the conference, and he gave this principle of rationality. So his architecture, by the way, is Act R. It used to be Act Star, but the principle of rationality changed it. So the R in Act R stands for rationality. This principle is that cognitive systems, the adaptation of its behavior for the organism, whatever you're modeling. And so optimization is, well, yes, it depends on how you would define that, but essentially we adapt our behavior to learn and improve when things occur in the world. And he gives, for the kind of for this principle, under this principle, when you're wanting to use a cognitive architecture, you first have this rational analysis. The first three steps are to specify the goal that you're trying to model for this cognitive system, the set of goals for the behavior that you're modeling with the architecture. You develop a formal model or a computational model of the environment that the cognitive system would be within, and make some assumptions about the computational cost, right? There's not only a cost to behavior, but there's a cost for thinking. And given those first three steps, you then derive a function for that, or a model in the architecture of that behavior. So your behavior might be planning, or your behavior might be text understanding, or it's something more narrow. For ACT-R, I believe they also looked at modeling human reaction time and memory experiments. So it might be simply memorizing a list of 5 words and then recalling one word that may or may not have been in that list after so many seconds of seeing it and then not seeing it. So that might be the behavior that would then be modeled. You then test that and either confirm or disconfirm the kinds of predictions that come from your model when you look at how people would do it. And if there is a discontinuity there, you would iterate and try to improve what your assumptions are, your formal model, what goals, how their goals are represented, or exactly what the goals are. You have ways to just iterate on that. Given that, then ACT-R has this kind of a structure. It focuses on memory in terms of a declarative and a procedural memory. Declarative memory being the memory for facts or concepts, or skills or behaviors, or how to do an action would be our procedural memory. How to ride a bike is less a step-by-step, well, I raised my foot by so much, it's whether I can just perform that. And so there's a long-term memory for both declarative and procedural, and that you can retrieve from or execute items from memory. You have a working memory from within. You do matching to your long-term memory to have to retrieve items for performance given some input encoding. There's a sensory register where the input comes from. So this is an abstraction too. There are a lot of details. The model is in a production system, or it's rule-based. You define the rules. That's kind of like the programming language for a computer architecture. Here you would define the rules for the behavior model that constitutes the behavior model. And then those rules would be matched from memory. You retrieve them and then execute the rules for behavior and see how it would operate given input from the performance. So now that touched on, he had a cognitive architecture. He talked about a cognitive system. There it was a little bit synonymous. In a very interesting paper, though, later in 2009, that Anderson paper was 1991. Here, Langley and Laird, John Laird and Pat Langley and Rogers had a very good paper about cognitive architectures, and they defined it in terms of 3 characteristics an intelligent system, or for the agents. So the cognitive architecture specified a fixed domain independent infrastructure that consisted of memories, both the short and long term, memories that store knowledge or content about beliefs, goals, and knowledge. The representation, how those elements are actually represented in the memory for larger scale structures and how they're composed, and then the functional processes that actually operates on the knowledge that would produce an output given some input. So those are three important things I think you will find in all architectures, either more or less. For us that are in the MIDCA community and that are intimately familiar with MIDCA, the representation, for instance, that we would have for a shop operator or to create a domain, the documentation helps explain that. And we know Dustin went through the functional processes, but the memory model here is actually weak in MIDCA, but that is something I think that is forthcoming, where it's highly developed in most architectures and a large focus. Here we have SOAR model. You can see again a procedural memory in long-term memory, also semantic, and then episodic. So semantic memory is like an ontology, the concepts that we know about. Procedural, again, is the skills that we have. Episodic it's a memory of the actual actions that the individual performed in the past or currently, and we would store that. And it also has a symbolic working memory. It has a very sophisticated spatial visual system that has been connected with camera systems and robots in the past, and produces action. So there's a lot of similarity here. Unlike Act R, what is modeled is often not necessarily human data, and certainly usually higher level cognition and performance, for instance, on a robot behavior rather than reaction time studies. It's at a little different level than Act R, but there are a lot of similarities there. Icarus also contains a number of the same things, a memory for concepts. This is a declarative memory in beliefs. It has a perceptual buffer as well. Skills here are distinct from concepts, but are represented in the same language or the same representation here. So there's it's slightly different, but very similar to the others that we've seen. Then there's a separate architecture definition by Ron Sun. He has a architecture called, but this is a very similar definition as well. He says that a cognitive architecture is broadly scoped, it's domain generic or domain independent. It's a computational cognitive model and captures essential structures and processes of the mind to be used in broad, multiple level, multiple domain analysis of behavior. So I think that is very consistent with what we've seen both in the principle of rationality, previous definition. Here, Ron Sun does distinguish, though it's not in this quote, it distinguishes between implicit knowledge and explicit knowledge. So I can show you that. This is Clarion. There are four main parts. There's an action-centered subsystem about behavior and skills and so forth. There's an explicit representation of actions and implicit representations. This is the upper left in blue. There's also non-action centered explicit and implicit representation. This would be for concepts, and instead of about behaviors, it could be about new concepts and learning facts. You would, for natural language, I believe that would be in this component. You also have a motivational system. Now, this is the lower left, in which goals originate from. So there's both an explicit goals that are structured here, and there are implicit goals that emanate from drives of the system, basic drives. And then there is a metacognitive subsystem. So as Dustin mentioned, there is a commitment to metacognition also in this dual cycle architecture MIDCA. It is different here. The system, I believe, is subsymbolic or neural net based. The The implicit representations in Clarion are neural nets. The explicit are rules, again, like productions or a rule-based system. So there's still commonalities. There is this is one of the architectures, other than MIDCA and Clarion. I think few really look at metacognition specifically. What is done in metacognition here is, as I understand it, it's more about goal setting rather than originating the goals. I believe this is selecting the goals. It's similar to the intend function. More information can be found at the URL below at Rensselaer Polytechnic in New York. So I wanted to switch to our take on cognitive architectures and all of this cognitive agents and related concepts in the MIDCA, the little MIDCA community that we have here. And I can think of it as, my thought was to think of it as a perpetual goal-driven cognitive agent. We have less of, I mentioned, we have less of a commitment to human data per se, but more about agents that do things in the world, whether it's a robot or a model of a human. I don't think we're all about robots alone, even though, oh, and that was, by the way, the thing I forgot in the mini, one of the new things was the interface to ROS. I think that was really implemented this year. I'm not sure that we had it at last year's workshop. We did have it already by then. Okay, so I stand corrected. Anyhow, I did want to make a plug to it. But let me go back. If we're saying a perpetual goal-driven cognitive agent, what do we mean actually? Instead of a cognitive system, a cognitive agent, well, I would claim, well, actually, Hewins and Singh claims a cognitive agent is some intelligent system that uses knowledge structures, goals in an environment in which there's perception and action. So agents are ones that find themselves in some environment, whether it's a software or a physical environment. It may be a software agent rather than just a robot, but there's some environment rather than just mind games. It's embodied in some sense. And then goal-driven autonomy. There's a real commitment from this notion of what we call here goal-driven autonomy and more broadly goal reasoning in the MIDCA community. And I think this is one of the places where it started. And that's one of the focus of the metacognitive or the MIDCA architecture is that we don't just wait to be told. Agents, a MIDCA agent can generate their own goals given some anomaly that it would perceive. So it can recognize when there's a problem, possibly explaining what caused the problem, and then generating a goal to remove that cause. And there's some citations here that can point you to more about that commitment. But perpetual, perpetual is simply just agents that would exist over long durations. And we've had some work. It would be, I think the ideal would be to have an agent turn on the robot and have MIDCA use it for a month. John Laird wanted to have a SOAR agent that had a memory of behavior over a year. And I'm not sure, but with the episodic memory that they worked on a few years back, they did have extremely long episodic traces or memories of continuous action. We have not done that kind of experiments like that, but we have put in place, and we, I think the the algorithms or the procedures, and certainly have thought about what it takes. That drives our research. It really, if you have a long for which an agent needs to be independent, things will happen that they don't expect in long durations, and you need to be able to react to that and manage it without to avoid catastrophe. Then this was the architecture. Dustin talked about it a little bit. I wanted to point out one very minor thing. I think his architectural diagram was from a little bit from last year. So in the perceive phase in the lower right in orange there, rather than claiming that this would be outputting a percept, I think within that, we would have a perception from the environment, and we generate out of perceive is a state in terms of predicate relations. If you're working with Ross in the environment, that's a very big problem, actually. Zora's, Dannenhauer's work has distinction there, and it's a minor one, but I just wanted to point that out. So as a cognitive architecture, as a cognitive system, or as an agent, I think these are the main points in which MIDCA makes the connections to other work in these related research areas. The 6 assumptions of a cognitive system, other than I had pointed out, it's a weak link to human data, more inspired rather than trying to model human data. I guess, well, that was in the principle of rationality, but the 6 assumptions for a cognitive system were generally met. It adheres weakly to the principle of rationality. We do focus on what the representation is and what the processes are, what the function of those processes are, that is their input and their output, and what is the transition, and but not memory per se. The 2 big points, how many minutes? The 2 big points, though, is that the MIDCA architecture really constitutes a computational theory of high-level autonomy, what it takes for an agent to be independent, generate its own goals, not wait to be told what to do. And secondly, it does center on goals and metacognition in particular, and I think that distinguishes it. But I can't emphasize more of the commonalities with it. These are the conclusions I think I've gone over. And to be on time, Robbie, you can come on up. Just to reiterate, there's a lot of commonality here, and we do share with all cognitive architectures. We differ. There were a number of examples that we covered, and hopefully we will have coming out in this following year a version 2 of MIDCA. We shall see. Thank you.
Thanks, Mike. So we are now going to transition to Shravia's talk. So just bear with us a moment as we yeah, so just gonna screen share and just gonna all right. Okay, so I'm gonna pass this over to let me just go back to the Google Hangout, make sure, okay, everything seems to be working. Okay, please welcome Shravia Kandrakunta. She's going to talk about goal graph and goal operations in MIDCA.
Hi everyone, I'm Shravya and I'm going to discuss a few points about goal graph and goal operations in MIDCA. So let's get started. Goal graph. A goal graph is a data structure which organizes and manages all the goals of the agent in a hierarchical format or a tree structure. The current goal graph in the MIDCA has three classes associated with it. The first one is the goal, the second is the goal node, and the third is the goal graph. The goal contains ID and arguments, which means the ID is the predicate of the goal and the arguments are the objects related to that predicate. And then the goal node contains 4 objects within it. The first one is the goal, the second one is the parent set, the third one is the child set, and then the children set, and the fourth one is the plan to achieve the goal. And then the goal graph contains all the relations between the nodes. That is, it might be a single node might be a parent to some other node, or it can be a child to some other node, and all those things. So the goal graph structure helps the user and as well as the agent to prioritize all the goals which it has. So let's take a look at how the goal graph is working. So whenever the MIDCA is initiated, initialized. An empty goal graph is also initialized with MIDCA and is inserted into the memory of MIDCA. And whenever these new goals are inserted or inputted by the user or by the agent, the MIDCA performs goal validation on those goals, to check if the goal is really valid one or the correct one. And then if the goal passes the goal validation test, then those goals are inserted into the goal graph in the memory, and later on fetched from the memory, acted upon, achieved, and then removed from the goal graph. So let's take a look at this in detail with the help of the MIDCA architecture. So here the perceive phase does not have any interaction with the goal graph. It just currently observes the world and updates the states of the world into the memory. The interpret is the one which gets all the goals. Those goals might be the user provided one, or generated by the agent itself. And then the interpret only validates the goal based on by checking the ID and arguments of the goals. It initially checks if the ID belongs to the domain file defined in MIDCA, and arguments are already in the state file or not. And if these two tests are passed, then the interpret goals, then the interpret phase inserts the goals into the goal graph and stores it in the memory. And then the evaluate phase checks to see if the goal is achieved or not. If the goal is achieved, then the evaluate phase removes the goal from the goal graph. And the intent phase is where the goal selection operation happens. We'll talk about the goal operations in the next few slides, but just to make sure, the intent gets all the goals from the goal graph, and then selects some goals based on some criteria, and inserts those selected goals into a stack called current goal stack. And then the plan gets that current goal stack, and then checks to see if a plan already exists for that current goal. If not, then it would generate a plan and insert it into the goal graph. If a plan already exists, then it does nothing. And then the act phase iterates through the plan and executes each action at a time. And in the meta phase, in the meta phases, the also interacts with the goal graph in order to perform the goal transformation operation, which we'll talk in the next slide. So if you want to better understand the goal graph working with the example, please take a look at the previous year's demo. It'll be more clear than here. And so here are few goal operations which are already implemented and are yet to be implemented in MIDCA. The first one is goal formulation. The goal formulation is when the agent generates its own goals without the help of an external user. The goal selection operation happens when there are more number of goals to achieve in front of the agent, and it is not in a state to achieve all of those. And then the goal transformation operation happens for several reasons. One of the reason is the lack of availability of resources, and the other reason might be some other goal is more important to the agent than the goal it is working on. And then the goal delegation is the operation of the agent delegating its own goal to some other agent or the user himself, because it comes into its knowledge that it is no longer in a position to achieve that goal. And then goal achievement checks to see if a goal is achieved or not. And then the goal monitoring, this is the work of Zora, and she's currently working on it. It checks to see if the reasons to achieve the goal are still valid or not. So let's go into detail. Let's talk a little bit of detail into about some goal operations here. So the goal selection operation, as I said earlier, this happens when the agent has a choice of multiple goals, and it cannot achieve all of those. So after knowing this, we come to a question, and we come to a question on what basis do I choose. So here in MIDCA, we have used we have implemented this of performance to limiting factor, where the performance and limiting factors are domain specific, but the estimates of the performance and the limiting factor are estimated by the agent, uh, uh, by the by the agent. We call this smart selection criteria. You and This idea is borrowed from Johnson. His work was very domain specific, and we tried to generalize the work to different domains. Let's take uh, look at a specific example to better understand this criteria. So here, let's take a look at the construction domain example. Here, the agent has two goals: to construct the building B1 and the building B2. So for each goal it achieves, it would be given a credit, say 1, and the limiting factor here is time, and the agent should complete all of the goals within its time limit. So to be more clear, to place the block A, the score it would achieve is 1 here, and then the time taken to put the block would be 1, and for the B and also the block E, the score would be 1 and the time taken would be 1.2, and it is the same for the other one. And as the height of the tower increases, the time taken to place the block also would increase. The time and the score are currently provided by the user. So if we take a ratio, the ratio of performance over the time for building B1 would be 0.88, and for the building B2 it would be 0.9. And if the agent had all the amount of time in the world, there is no need of this goal selection operation, because the agent could do each and every could achieve all of its goals one after the other. But in the real world, this would not be the situation. So let's say if the dead if the agent is asked to perform to achieve these goals within a deadline of say 5 seconds, then then the agent is forced to perform the goal selection operation. And in our method it would select the building B2 because it has the performance over time. Earlier it was the minimum ratio, but then we changed it to the maximum ratio in order to maximize the performance rather than uh, checking it for the time being. Oh, sorry. Okay. So that was the goal selection operation. And the goal change operation, this currently is implemented in MIDCA whenever the MIDCA is out of the resources, or whenever the MIDCA encounters any emergency situations like the tower being on fire or something like that. Uh, so even this is implemented in construction domain. So we would call that a tower is stable when the tower is constructed with the help of motor, and we would say the tower is not stable or wobbly if the tower is constructed without the help of the motor. So this is implemented in the control phase, that is the meta phase of the MIDCA. So the MIDCA would be given a certain number of motors, and then it would be asked to achieve all sturdy towers. So it has to use only the stable ones, after certain time it would be out of motors, and then it has to it would be out of motor, and it would be left with any choice. So there comes the goal change operations, and then the agent would itself change the operation of stable on to on, and then complete the construction of the tower without the help of the user directing it to change its goal or anything. So we have implemented this goal change operation using predicate transforms, where the generalization means moving into more generic predicates, specialization means moving into more specific predicate, and identity means uh, stay selecting the same goal again. And abstraction is similar to generalization but for objects, and concretion is also similar to specialization but for objects as well. So this is how, with the help of predicate transform, we have implemented the goal change operation in MIDCA. And the one more important operation happening in MIDCA is the goal formulation. MIDCA is able to formulate its own goals whenever it encounters an anomaly. This happens in interpret phase of the MIDCA. Whenever a block is set on fire or something, then the MIDCA generates its own goal of putting off the fire, and then it gives it the highest priority. Uh, so that's it. So let's take a look at the future work here. We are wanting to introduce a new variable or something called goal type, which would say which would associate the type of the goal into the goal graph. We think that this, with many other factors, would help in integrating or making the goal operations more flexible. And we also want to make the all the goal operations work simultaneously. Currently these operations are implemented, but all of those are independent of each other. And these are also domain specific, and we are trying to bring everything to every domain uh, till now. And so that's it. Thank you.
Thank you, Stravia. So we are now going to get ready for our first remote speaker, James. So, James, are you there?
Yeah, can you hear me?
Okay. Yes, we can hear you. So I'm going to go ahead and pass over. Are you ready to go?
Yeah, I'm going to work on the screen share. Hold on 1 second.
Okay. I'm going to give you the. I'm going to make it so that you're presenting to everyone.
Okay. All right, can everyone see this and hear me?
We can see you and hear you.
All right, you can see the slides?
Yes.
Okay. So I'm presenting on how we've been using MIDCA to enable intelligent rebellion in autonomous agents. It looks like I'm the first one that's more of a separate application and less of the structure of MIDCA itself. So I'm James Boggs. I'm an undergraduate senior from Union College in New York. And I've been working with Alexander Coman and then Dustin Dannenhauer to do some intelligent rebellion and rebellious agents kind of work. So rebellion, it's sort of sketch. A lot of people go, why would you ever do that? That's how we get Skynet. But actually, rebellion is kind of useful. So a rebellious agent in general is one who rejects an operator's command or order. So humans can be rebellious agents too. And in real life, we often are rebellious agents. So in real life, we rebel when we see something going wrong and we say, actually, no, I'm not going to do this because it's going to lead to a bad result. Problems with what we're doing. So I'm not going to do that command because there are ethical problems. I have an issue with what you're telling me to do. I won't do it. And then there are things like self-expression. When you say, I personally just don't appreciate that. That's not the kind of thing I want to be doing. What you're telling me to do. And robots can get sort of similar benefits to that by rebelling against certain goals, if we can get them to rebel properly. Rebellion is useful in real life. So consider some rebellious situations when a human might be rebelling. And I'm taking a lot of these examples from a paper by David Aha and Alexander Coman in 2017, which sort of presents a motivation for rebellion. So in one situation, an actor in a high school film project is arguing with her director about the way in which her lines should be delivered. So the actor, having practiced the role and understood the character, is in somewhat of a better position to understand how the character is feeling and thinking at the moment. And so by arguing and rejecting the director is directions on how to deliver a line and imposing her own ideas of how the character should deliver the line. She's actually enhancing the character's believability because she has a pretty good understanding of the character's background and motivations. So that's a net benefit from her rebellion. Then maybe early on in her career, an employee expressing her preference to like not take on a new position or to not get a new management position, for example, can be sort of an instance of self-actualization where the employee says, I don't see myself as, maybe the promotion is to like a manager. I don't see myself as a manager. I want to learn more. I don't feel like I'll get much out of the position. And so she rejects a promotion or take up a different position because she doesn't feel like that really fits what she's looking for in her life. Then ethically, imagine that she's an established engineer and she's working on this project and her supervisor is telling her to hurry up, to hurry up the pace. But she recognizes that if she puts it out too soon, there will be flaws in it, which could lead to danger to people's lives being lost or at least to damages. And so she refuses. She says, I won't work on this project anymore if you're not going to give me the time I need to do it properly. That's sort of an ethical rebellion, which obviously will have benefits because people won't get hurt if the project goes wrong. And then there's sort of a social aspect. So imagine that she sees a social wrong, so she can lead a social protest campaign in support of her in-group or another person's in-group, which she feels is being wronged or being subjugated in sort of a social justice situation, which is a sort of a rebellion against society and ends up improving life for people in that group. And in these situations, the human is rebelling, and it's a clearly beneficial rebellion. This is the kind of rebellions that we want to encourage in humans. And I think there are similar situations in which a robotic agent rebelling gets some benefits. So there's not a whole lot of background research on this. It's a fairly new research area. Aha and Komen note that the formal framework for AI rebellion doesn't exist yet, and that was in 2017, so that's fairly recent. There is some motivational work and example scenarios for rebellion, and the ones I actually cited in the last slide were from the AI rebellion, Changing the Narrative, the Aha and Komen 2017 paper at the bottom there. But there are several other papers that you can find good examples of why we might want to investigate intelligent robotic agent-based rebellion. So the topic of the topic of the conference is why MIDCA and how do we use MIDCA? So we started out with MIDCA because it's Python-based. I already knew the language, which is a big help. But there are also, of course, lots of libraries. It's easy to test and prototype in Python. The benefits of Python, you can go online and there's all kinds of nigh on religious stuff about how Python is so good. But it's also metacognitive. So it's focused on introspection on goals and figuring out at a meta level which goals are appropriate and how we might want to change goals and change the way we're thinking about goals. And that seems to be where rebellion fits for me. I see this as a very natural place for rebellion, is at a meta level, considering the goals themselves with a sort of a meta goal of being true to yourself or being ethical, these kind of things. It's also modular, so that was a huge benefit. It means that we don't have to, as I believe Dr. Cox mentioned, it's a framework, it's an architecture, so we can add things in, we can create modules without having to redo or recreate an entire framework for it to create a skeleton. So it provides us a baseline, and then we can just add in new modules that enable rebellion without worrying too much about the inner workings. So in our rebellious agent, MIDCA is used as the agent, as the base agent, and the rebellion itself is currently happening in the interpret and evaluation phases, which is not at the meta level yet, but that's kind of where I felt it fell naturally within just the cognitive layer. And at the time we started working, the metacognitive layer was still under development. So we added some rebellion modules, which mesh pretty well with the existing MIDCA code that we found in the code base. We did rewrite most of the other modules to fit in with a new scenario, but it was essentially just adapting some of the modules that come with MIDCA to our new domain. It wasn't particularly strenuous. The interesting part was definitely the new modules that we developed for Rebellion. MIDCA's memory and goal graph, the access to these kind of tools was really important to us. So that was a huge part of our usage of MIDCA was with these things. And then again, MIDCA's modularity, the ability to create modules which enable rebellion without worrying about other things like perception, planning, and acting. That was a big benefit. And that was part of why we used MIDCA. So here's kind of a diagram of how rebellion works. I know it's pretty standard MIDCA. So the important part starts at the interpret phase once the agent has already had a perception of the world. And the agent interprets this perception of the world in light of goals and evaluates, and then can evaluate how goals need to be adjusted or changed based on this interpretation. This is pretty standard MIDCA stuff. And so up to there, we're about the same. But part of the interpretation is now appropriateness. It's not just how are goals physically affected in terms of its ability to complete them, but how have goals been affected in terms of its willingness or the appropriateness of a goal to be completed. So we can evaluate this interpretation and decide that each goal is acceptable, in which case it goes ahead and plans and acts and carries out the goal, or impossible, in which case a goal, or it might remove the goal from the goal graph. But that's also a fairly standard thing. But it also might evaluate a goal to be undesirable. And that's kind of where rebellion comes in, because the goal is still possible. It could carry out the goal, but it might not desire to carry out the goal. And that begins the rebellion part. And so as part of the rebellion, it sort of evaluates why it's rebelling. It looks at the goal and remembers the goal, but it also looks at like the scenario surrounding the goal, what caused the rebellion. There are multiple operators, gave the goal that it's rebelling against, information that you can use to glean why and what it's rebelling against. And it gathers all that up, and then it actually informs the operator who gave it the goal. Critical part of rebellion, of useful rebellion, is a dialogue between the agent and the operator. And the operator, it informs the operator of its rebellion, and the operator can then accept or reject the rebellion. So if the agent rebels and the operator says, okay, that's a good idea, we shouldn't do that, you're correct to rebel, it just goes on and removes the goal from the goal graph or adapts it into something which is acceptable. If the operator says, no, you can't rebel, I'm forcing you to do this, then the agent actually has a choice, because the agent is ultimately the troop on the ground, or the actor in the situation. So the agent can actually still rebel. It can consider this rejection from the operator. And if it rejects the operator's dismissal of its rebellion, it can still remove the goal and say, I'm just not going to follow your directions at all. But it could also say, well, my operator is really enforcing this, so I feel like I must go ahead and do it, even though I have reservations about the goal itself. And then it accepts the rejection and goes ahead to the plan, the intention, plan, and action phases. So there are two phases that are particularly important and have come up a bunch in the rebellion: the interpret phase and the evaluate phase. These are both part of MIDCA itself. They are inherently very surprising, but we've added a little bit to them. So the interpret phase in MIDCA, it normally interprets the world in light of its goals. It looks at the percepts that it just got, says, all right, how have these affected the goals? Rebellion adds appropriateness as a thing. So in addition to impossibility or the needing to change a goal, it also says its goal is inappropriate. The evaluate phase is then used to look at how goals should change in light of interpretation, how we can alter goals or come up with new sub-goals. Rebellion adds agent-operator interaction as a means of sort of judging whether a goal is really worth rebelling, or figuring out how we can adapt a goal to make it less undesirable and more appropriate to carry out. So the interpret phase in particular, as I said, MIDCA uses it to interpret how new percepts may affect the goal. Rebellion, in this case, is whether a new percept has changed whether a goal is appropriate or not. So in our domain, we model agents as military drones and operators as sort of troops on the ground who are instructing these drones. And so if a new percept says, oh, there's a civilian in the area, that might impact the ethics of its goal to eliminate a target. And it says, oh, this isn't appropriate anymore, and then it passes it on. It remembers that this particular goal has a problem with appropriateness in particular, and it moves on to the evaluate phase, which like normal MIDCA is used to evaluate the status of goals and kind of resolve the problems either by removing the goal or by changing it, reevaluating it. And the rebellion that's inappropriate are now evaluated into how can we make them appropriate, or do we have to just get rid of them? So once such a rebellious goal is found, or a rebellion-inducing goal is found, the agent can sort of evaluate why is it worth rebelling, what is the agent specifically rebelling against in this situation, and then inform the operator. Because we want the operator, again, we want the operator to be party to this kind of rebellion. We want the operator to have some amount of say in why isn't it appropriate, what can we do to resolve the appropriateness of the rebellion. So if a goal which was interpreted as killing a civilian, which makes it inappropriate, there might be alternative goals that the operator is aware of, and it's rebellion worthy, and then they can communicate about this. So there are actually two parts here. First thing is establishing the rebellion, which is figuring out why it's inappropriate, analyzing the situation, gathering all of the information which the agent uses to make its decision to rebel, and any information which might be useful in altering the goal and creating a new goal. And then it communicates the rebellion with its operator, including all the relevant information, any kind of new goals it's come up with on its own, and then asking what it should do, whether it should actually rebel, and what it might be able to do in the future. So this communication, I'm kind of speeding through here because I want to get us a little bit back on time, but this communication is enabled in our instance using TCP, which I added on here just because it's an interesting thing that I haven't heard about with MIDCA. But essentially, we wanted each MIDCA agent to be running separately and removed from the world. So there's a few benefits to having them operate in separate processes. At the core, it isolates the world information from the agents. So the agents have no direct access to the world information. The interface between the two over TCP really allows us to control exactly what the agent can see and what they can do. And this makes it much easier to implement partial observability. And it also kind of makes it more accurate to the real world. So in real life, of course, the agent and the operator aren't on the same local machine. They're communicating over a network somehow. And there's only so much that information that the agent can communicate to the operator at each given time. So we added some TCP communications into the modules themselves, which can pass actions or messages from other agents or even observations about the world back and forth. So the way this kind of works is that the world is a server, a TCP-based server, and each agent can pass requests back and forth to the server. Things like, what does the world look like to me? Actions, I want to do this in the world, or messages to other agents, like I want to tell my operator that I'm rebelling. In the future, we might look at adding a more robust kind of communication system outside of each individual model, that modules can access similarly to the way that they can access memory or the goal graph, things like that. But I just thought that was an interesting aside. So our actual research imagined military drones as the rebel agents in question. So kind of agents or operators in autonomous situations, and the reason for the rebellion is ethical rebellion. So a rebellion happens in these situations when the agent sees a civilian that's threatened by their goal, where their goals are usually the elimination of enemy targets. And you can imagine that from drones, the possibility of harming a civilian when they're eliminating an enemy target can be kind of high sometimes. And that's like ethically very worrying. So they are programmed ahead of time with the ethical desire to not harm civilians. The world itself is fairly simple. It's just an n-by-n grid where we portray agents, enemies, and civilians, and they each take up a tile. And agents can actually fly over enemies and civilians and be on top of them. And the agent can detonate a bomb at its location, which has a certain radius of effect and eliminates enemies and civilians in that radius, starting from where the agent itself is. So it's aware of how far its blast will spread and which enemies and civilians are targeted. The operator is stationary. It doesn't actually see any civilians. It knows where the enemies are and can give goals to the agent, which introduces some amount of uncertainty and kind of motivates some of the rebellion aspects. itself will just give a goal